So let us see some of the parameters and equations that are necessary and whenever we are going for the kinetics of radioactive decay. Just a quick review, by the way. And of course, next we're going to look at some of the examples actually related. So let's start with a time. A time is symbolized as actually T. And this is the time required for actually a radioactive substance to decay. It can be given in seconds, let's say hours, let's say minutes, can be days or actually years based on the nature of the actual radioactivity. You should know that. And we also have what you call should be a Lady constant. So it should be a Lady constant. So a Lady constant, some books it is being symbolized as K, and the others they actually symbolizes it as actually lambda. So this one determines how fast the reaction has to be. So keep that in mind. And we also have what you call the initial content or initial amount. Initial content should be initial content or initial amount. And basically it is symbolized as A naught. And this is the amount of substance before it decay. It can be given in grams, a kg, whatever it can be, but it represents the initial amount. And we also have the final amount. Should be final amount or final content. So final amount, and this one is symbolized as any actually a subscript T. This one represents the amount of substance remaining after some time T. And we also have the half-life. We also have what you call the half-life. So what is the half-life? Now this one is symbolized as T subscript half. This one represents the amount of the time takes for the actually initial amount to be halved. That is the half-life. And we also have the number of half-lives. So should be the number of half-lives. The number of half-lives should be the number of half-lives. And this one is symbolized as a small letter actually n, and this one represents the number of half-lives until the actual substance actually decayed from the initial to some sort of the final. So that is. And we also have the fraction of remains, and which is symbolized as, we have it as the fraction of remains. And this one is symbolized as actually capital letter Y. So these are the parameters you should have to understand. And by the way, a fraction remains actually determines the amount of actually a substance remaining at the time T in terms of the fractions. And it can also be expressed in terms of, let's say, the percentage remaining, where you see how we should have to work out with that. But these are the parameters you should have to understand. And of course, let's see some of the formulas you should be very familiar with. And we have the formula for the half-life. Now the formula for the half-life, it is given as, half-life is equal to a time divided by the number of half-lives. So this is the formula for the half-life you should have to understand. And we also have the formula, so which means if we have the half-life and we have the time takes, we can be able to have the number of half-lives. Let's say we have the half-life and we have the Damptex. We can also be able to have the number. By the way, even if we have the Damptex and we have the half-lives, we can also be able to have the half-life. Let's say we have the half-life and the number of half-lives, so we can also be able to have the Damptex and using this formula. So keep that in mind. And we can also be able to have the fraction of remains, and which is given as, now we have it as 1 over 2 to the power n, where this is the number of half-lives. 1 and 2, these are actually constants, and this is the actual fraction of remains. So you can have that understand. Or else, using the same formula, you can also be able to have the number of half-lives if we have the fraction of remains. Keep this in mind. And also we can also be able to have the amount of, actually we can also be able to have the final amount using the formula given as the fraction of remains times the initial amount. So this is the formula you should also be able to understand much about. If we have the fraction of remains and we have the initial amount, you can be able to have the final amount using this formula. Likewise, if we have the final amount, we have the initial amount, we can be able to have the a fraction of remains using the same formula. So keep that in mind. And we can also be able to calculate the half-life using the formula. This is given as the half-life is equal to, should be a ln 2 that divided by the lead constant, that is given as k, or some books they uses it as a lambda. So keep that in mind. So this is equation number 4. You should be well to mastermind about as well. And we also have the actual equation that relates the Damptex, the half should be that relates the Damptex, the lead constant, initial amount as well as the final amount. And we have it as ln actually nt divided by, should be, that is to be given as ln nt divided by initial contents, which is equal to negative lambda times t. So this formula can be used to have, let's say, initial contents if we have the final contents, and we have the lead constant as well as the Damptex. So I can to see how we can have to make use of those equations, and for the time being. And these are the formulas you should be actually have to understand about on the concept of the actually kinetics of radioactive decay, actually, and for this case. So these are the formulas you have to understand. This is formula number 5 you should know. So let's just have to appreciate some of the questions you should have to expect, and from these actual formulas. So now let's say this is the question: how much of the original radioactive material remains after 4 half-lives? So what is the point of interest here? So now we are being given the number of half-lives, which is given as n, which is given as 4. Now we are looking for the how much of the original radioactive material should remains after 4 half-lives. The point of interest is the fraction of remains, since we do not have the initial active materials, but what we are only looking for, it is the fraction of the remains after actually 4 half-lives. So now what is the formula that connects the two? Now the formula for the fraction of remains is given as 1 over 2 to the power n, and of which we have the number of half-lives that will be given as 1 over 2 to the power actually 5. Now, which is the same as, what is 2 to the power 5? We have it as 32. We have 1 over 3 actually 2. That is the fraction of actually remains after 4 half-lives. And of course, in terms of the percentage, we can have it as times 100%. That could be the way to go. But this is how you should have to understand that one. And had it been that we had the initial amount, it means we could have been looking for the final amount upon having the fraction of the remains and times the initial amount. We're going to look at these cases and this kind of the concept in due course for this. So now let's say this is the question. How much of 56 radioactive sample radioactive remains after 3 half-lives? So now we have the initial contents, and that is given as 56 grams. And we have the number of half-lives. This is given as 3. Now we are looking for the final actual contents. That's what we are looking for. But now, since we have the number of half-lives, now the point of interest that we should have to calculate the final contents upon having the fraction of remains times the initial contents. Now in this case, we should have to solve the fraction of remains first. That is given as y is equal to 1 over 2 to the power number of half-lives, which is given as 1 over 2 to the power 3. That is given as 1 over, what is 2 to the power 3? We have it as 8. So which means we have 1 over 8. Now in order to have the final actual amount, you have it as nt is equal to now y times the initial contents. That will be given as 1 over 8, that is times 56 grams. That will be given as, now what is 56 divided by 8? So now we have it as 7 actually grams. So that will be given as the 7 grams. This will be the amount of this will be the amount remaining after should be 3 half-lives. And on the same case, but anyway, that's how you can have it in that way. And let's see the next question as well. So let's say this is the question. How long is a half-life? So which means we are looking for the half-life in that way. For a substance that has 2.5 half-lives, so which means we have n, that is the number of half-lives. And every 50 years, that is the given as the time. 50 years. So should be that. So now, what is the formula connects the 3? So the formula will be given as the half-life is equal to, that is the time divided by the number of half-lives. We're going to use this. So now for this question, we have 100 grams unknown radioactive substance has a half-life of 4,000 years. We have the initial contents, that is 100 grams, and we have the half-life, that is given as 4,000 years. Now, how many grams of the radioactive sample will remain? So which means we are looking for the final actually amount. And given that the time takes, it is given as 20,000 years. Let's say that is the case. How should we have this? Of course, we may think of using this formula, by the way. That is given as ln nt divided by, that is which is equal to lambda actually t, and of which we have the time takes, and we have the initial contents, and we are looking for the time contents. But what is lacking here is the actual rate constant, of which the rate constant can be calculated using the formula given as the half-life is equal to Rn2 divided by the lead constant, of which with your calculator, what is the value of Rn2? You have it, and you have the half-life as well. You can be able to have the lead constant, and from there you'll be able to have the final contents using this formula. Or else we can also use the other formula as well we have recently discussed about, and of which we know that the final contents has to be given as the fraction remains times the initial contents, and of which how should we have the fraction of remains? Now the fraction of remains is given as 1 over 2 to the power n. Now in this case, the n is the number of half-lives. Now how should we have the number of half-lives? So the number of half-lives can be calculated using the formula given as the half-life is equal to, should be t divided by n, of which we have the half-life and also the time takes. You can be able to have the number of half-lives in that way. From there you'll be able to have this upon substituting the number of half-lives. Then you substitute here. Since we have this, you can be able to have the amount of a substance remaining after 20 years. So that's how best you can go for that. Let's say we have this case. So let's see the beauty of these questions. Now, if a substance starts with, should be 400 grams, that is the initial amount, 400 grams. And how much remains? Now we are looking for the actually a final amount after 6 half-lives. So now we have been given the number of half-lives, that is given as 6. So now how should you go about it? And of course we understand that the formula for the amount of a substance remaining after some time, and if we have been given the number of half-lives, has to be given as the fraction of remains times the initial contents, and of which we have the initial contents, and what we need is the fraction of remains, and of which the formula it is given as the y is equal to 1 over 2 to the power n. So that is the beauty of that first question. That is the question number 4. That's the beauty of it. And how about the other question? Now, how many complete half-lives? Now we are looking for the number of half-lives, and occurred if 12.5% of the original radioactive material remains. And that should be, now what we have been given there, it is should be the fraction of remains. That is 12.5, that is percent, or can be given as 0.125, that is. Now we are looking for the actual number of half-lives, of which the formula has to be given as y is equal to, that is 2 to the power n. And since we have this, we can be able to solve for n. So try to have that out at your own space, that is. And our question of number 5 actually 6 says that how many complete half-lives? Now we're looking for the number of half-lives, and have occurred if 18.7 grams of originally 600 grams radioactive material remains. So which means we have the actually a final contents, that is NT, that is 18.7 grams. So there is need to have the deeper understanding of the two actually parameters of the two values. Now, which means the initial contents, that is the original, it is given as 600 grams. Now we are looking for the number of half-lives. So how should you have the number of half-lives? So now the number of half-lives will be given as, using the formula, that is 1 over n to the power, should be 2 to the power n rather. Should be 2 to the power n, 2 to the power n. So what you'll be looking for it is that one, and of which the final contents, it is given as the actually fraction remains times the initial contents. You'll be able to have that and put it here, so for actually in there. So keep that in mind. So of course there are several questions you should have to come across with, but these are the formulas you should have to understand. So don't forget to subscribe to this actually YouTube channel for you to have an update on whatever the contents has been created. Thank you.